Welcome back to Math 135. We're now going to start with Lesson 21. We, in Lesson 20, talked about exponential functions, and today we get to do some interesting applications. Okay? And so, to get started, I have, you're investing $5,000, 12%, compounded annually. Put that in a different color because that may be a new term to you, and that's going to be an important thing for how we do the problem. And we're going to leave that money in for 1 year. And so the question is, how much do we have at the end of 1 year? Well, if you know anything about what compounding means, it means that at the end of that year, since it's compounded annually, at the end of that year, they're going to compute my interest, add it into the 5,000, and I'm done for the year. Okay? Now, how do I find interest? Well, in case you forgot, I put in our little favorite, I equals PRT. Okay? Now, you might say, oh, but that formula is for simple interest, so I wouldn't use that now. Oh, but compound interest is really simple interest happening time and time and time again. So I can actually carefully use my simple interest formula in order to do a compound interest problem. And especially in this case, because I'm only getting interest one time, which is essentially a simple interest situation. So my interest would be, my principal is the amount of money I've invested, the interest rate, and we need to put it in decimal notation, so it's a 0.12. Now your time and your rate must be consistent with their units, meaning that if you're going to have an annual rate, then your time must be how many years? Okay, in this case it's 1 year. All right, well I think if you do that arithmetic, you get $600. So how much do I have at the end of the first year? $5,600. And I'm just going to make a little note here. When I compounded it annually, I got $5,600 at the end of the year. Of course, that's taxable income. Now, what if we're going to do the exact same situation, only you go to a different bank. And at this bank, they will compound your money semi-annually, which means twice a year. After 6 months, they're going to compute your interest and add it in. Okay, so like this. My interest for the first 6 months is my principal, $5,000, that's how much we put in, times the rate times the time. Now, remember, since this is an annual rate, I must put my time in terms of years. And 6 months would be half of a year. Okay, so when you compute that, you end up with $300. Which, by the way, does kind of make sense since we got $600 for a full year, that we got $300 for a half year. Okay. Now, what are they going to do with this $300? And by the way, when we're doing these problems, you're going to just set the money there and walk away and let it grow. So they're going to add, they being the bank, they're going to add $300 into your $5,000, so you now have $5,300 in the bank. So for the next period, we have $5,300 times 12% times another half for the second half of the year. So let's see here. I think that will give us $318. If I did my arithmetic correct, and you can check me on that, which means that at the end of the year, they're going to add this 318 into the 5,300, and we will have 5,600 $18. So on semi-annual, we have $5,618. Why did we get more money? Well, you'll notice that it really happened here in the second interest period, because in the second interest period, not only did we earn money on the $5,000 that we put in, we also earned interest on the previous interest. That's the idea of compounding. Earning interest on that interest means that you have more growth. Okay. Well, then I kind of like that compounding semi-annually instead. Well, let's expand that and go to compounding monthly. All right, so my beginning balance is $5,000. That's what we start out with. And so I'm going to use my simple interest formula. I have $5,000 times 12% times, now what's my time unit going to be? Since this is an annual rate, my time has to be in terms of years. But it's only for 1 month, so that would be 1/12 of a year. Okay, so we need to take 5,000 times 0.12 times 1/12. And what do we get? Well, I think we get $50. And what's the bank going to do with that interest? Add it in. So at the end of the first period, we have $5,050, which is what we have as our beginning balance for the second period. And in the second month, at the end of that month, they're going to compute my interest by multiplying it times 12% and then times another 1/12, because they're paying me interest for 1 month, which is 1/12 of a year. Well, I believe our interest is $50.50. And what are they going to do with that? They're going to add it in to what I already had. So I'm going to have $5,100.50. And that's what I started. Hey, by the way, isn't that kind of interesting? You can see that the second period I earned just a little bit more interest than I did the time before. Why? Because I earned interest on my interest. Okay. So $5,100.50, and I'm going to take this times 0.12 times 1/12. That zero's awfully puny, isn't he? Well, let's see here. The interest then that I earn, I believe, is going to be $51.01. 51.01. Hey, and you know what else is kind of interesting? You'll notice that we gained 50 cents in interest the first time. This time we gained 51 cents. Okay, now don't assume that you're going to play some pattern game here and make this easier, but it is interesting that what's happening is you're even gaining more each and every time. Not only are you earning more, you're earning it at a higher amount, if that makes any sense. Now, adding that in, I think we get kind of a cool number, 51, 51, 51. Yay. So, boy, are you having fun here yet? So we're going to do 51, 51, 51. Times 0.12 times 1/12. Why are we using the 1/12? Okay. And that ends up being $51.52 in interest. And if we add that in, we end up with 5203.03. Now, by the way, I'm not using a calculator and I don't have these all memorized. Do you know how this calculation is so easy to do? You know, who in the world pays 12% interest these days? Well, maybe you'll see it go back up at some point. The reason it's so easy is right here. What do you get if you take 0.12 times 1/12? You actually end up with 0.01. So I am effectively earning. Now watch what happens here. And I hate to give my secret away. I like to make you think I'm an amazing arithmetic person first. I can take this 5203.03 and effectively just multiply it by 1%. Because I'm getting 12% annually, then each month I'm getting 1%. I'm getting 1/12 of it, right? And doing that multiplication, I get 5203. See, the worst thing then is having to add, although this one's not so bad. So I've got 5255.06. And we can keep going and keep going. But you know, eventually you just get tired of playing this game and you say, come on, there's got to be something easier. Well, you know, with a calculator, because I'm not going to do this in my head, we can run from here, like let's start with the 5255.06. We can run from here straight over by doing one calculation, not figuring the interest and adding it in. Do you know what that one calculation is? If we simply take this principal and multiply it times 1.01, we'll go straight there. Why? Well, you see, here's what's interesting. When you read this number using all the good skills you were taught in elementary school, it is 1 and 100th. That is effectively 1 plus 0.01. Well, when I multiply that principal amount times the 1, I get back my principal. And then I multiply times 0.01, it gives me my interest. So in one multiplication, I can go from the principal immediately to my new balance. Hey, let me give you an aside on that. For example, if you go to the store, let's say the sales tax rate is 6%. And you buy something that costs $100. Now you see, what you can do is you can take $100 times 0.06, find out that your tax is $6 and add that on. And do 100 plus 6 and you get 106. Or you can take your $100 and multiply it times 1.06. And in one calculation, this is really a distributive property in arithmetic. You're multiplying your 100 times the 1 gets you your 100 back, and 100 times 0.06 gets you your tax. And so just like that, you've got your final answer. Okay? And we're doing the same thing here. And something else you notice is we could have started that way back in the beginning. So if you've got a calculator handy, grab it. Take 5,000 times 1.01. Here's what you get. Okay? Now, I don't know, this may make it really ugly here. So effectively, we're going over here and we're going to do times 1.01. Then you're going to take 50/50. Multiply that puppy times 1.01, and it's going to go right over to here. Are you seeing those numbers pop up? Then you're going to take this amount times 1.01, and there you go. And you know, pretty soon you start to realize I'm constantly multiplying by 1.01. That kind of makes me think of using an exponent. So I can go from here down to there very quickly on my calculator by doing 5,000 times 1.01 raised to what power? Well, you know, I told you in the last lesson, we don't have to see exponents as repeated multiplication, but that's one of their purposes, to the 12th power. So you run that on your calculator, and just like that, boom, 56, 34, 13. And I didn't have to find all those in-between amounts. I could go very quickly right there. Now, before we leave this, I really want you to pay attention to what's the point of having the 1 in there? The 1 gets back my $5,000. What's the reason the 0.01 is in there? Well, since it was 12% a year, and we're talking about a month, you divided that and we got 0.01 or 1% was our periodic interest rate. Why did we raise it to the 12th power? Well, because over a year we were getting our interest 12 times. Okay, so what's the shortcut? Because you see, what's really cool is eventually you learn how to do things more effectively. Human mind's amazing. Now, by the way, this is the Mrs. Blanton equation. I'm going to give you the textbook equation here in just a moment, formula, but I like this guy. And this guy is one that will stick in my head and make perfect sense for me to work through compound interest problems. My amount in the account is going to be my beginning amount. You'll notice in math, a subscript of 0 is almost always, at time 0, at the beginning. It's my beginning amount, or my principal, times 1 plus the periodic rate. We need that 1 to get back our beginning amount. This periodic rate is going to be how much I get per month or per semi-annual or per annual or per quarter or per day. And then raise it to the number of periods. So in my mind, A is equal to A naught times 1 plus periodic rate raised to the number of periods. Works in this one. Now, here's what you see in most textbooks. And by the way, this is your APR divided by N, which is the number of interest periods per year. That gives you your periodic rate. And since N is the number of interest periods per year, and T is the number of years, that would be the number of periods. Okay? Reason I don't necessarily like memorizing that is it may be just a lot of disjoint, icky stuff. You have to remember where all the letters go. You have to remember what all of those letters mean. Okay? But hey, whatever floats your boat, go for it. So what I'd like to do is use the shortcut to determine how much money we're going to have in the account. Now we're still doing the 5,000 at 12% APR, but we're going to change our time to 10 years. Now the reason is so that we can do some comparisons, all right? And if I don't use a pretty big number like 5,000, sometimes it's hard to see the variations. Okay, so the first thing we want to do is compute this annually. So using the Mrs. Blanton formula, for annually, it would be the amount in my account is going to be my beginning amount, which in the case of interest we generally call the principal. Principal times 1 plus my periodic rate. Well, now if I'm doing annual compounding, that means I'm getting interest once a year, so they're giving me 12% each time. And over 10 years' time then, how many times will they give me interest? Well, they'll give me interest 10 times, once every year. I'm not going to run that in my head. So I've already computed that out. It's going to be $15,000. That's pretty cool. I've more than tripled my money. I'm going to jot something down. If I have time at the end, I want to mention to you Rule of 72. And if I forget or we run short of time, you might want to look that up. It's kind of an interesting thing for your financial well-being. Now for semi-annual. For semi-annual, that's twice a year, right? Since I'm getting interest twice a year, they're not going to give me 12% every time. They're essentially going to give me half of that. They're going to give me 6% each time. Now, by the way, for those of you that are just not real comfy with that, remember that in my interest formula, I multiply principal times rate times time. And what we're essentially doing here is multiplying these two guys together. And I've got a 12% annual rate. And for semi-annual, my time is half of a year. And right there, when you do that multiplication, you see my 0.06. All right? And then in 10 years, I would actually get interest 20 times. Because it's 2 times a year, every year for 10 years. And that ends up giving me, oh, hey, I made another $500. That's kind of nice. $16,000. So you might say, wow, if Bank A is going to compound annually and Bank B is going to compound semi-annually, if I'm going to let it sit there for a while, I think I'll go to Bank B. Well, and what about monthly? Well, for monthly, we have 5,000 times 1 plus, and by the way, here's why I use the 12%, right? If it's 12% annually, then each month I'm getting 1%, okay? Hey, and by the way, it doesn't have to be just a savings account at the bank. It could be certificates of deposit. It could be a mutual fund that has a certain return rate. Now, of course, those aren't guaranteed or anything, but you might want to use it to just kind of see what would happen if I had a mutual fund and over a 10-year period, it was giving me 12% return. You do the same thing. Okay, well, how many times will they give me interest in 10 years if they give me interest every month? Well, that's 12 times 10. That's 120 times. And I'm really not going to do that guy in my head. So let's see. 16,501. So by the way, as far as the comparison is concerned, you might notice that going from annual compounding to monthly compounding, you gained about another $1,000. Of course, $5,000 is a lot to sit there. 12% is a huge rate. But you can see that it does have an impact. All right, well, what we want to do, and this is where you realize having this formula is so handy because I can very quickly come up with these values. We want to do the exact same problem, only we want to go to 20 years. Now, do you realize that the only thing that's going to change here, for an annual, it still is 12% every time they give me interest, but we're talking about 20 years. Well, if they compound it annually for 20 years, wow, that's kind of nice. Your $5,000 is up to $48,000. It's nice. Now, in the case of semi-annual, you're still going to get 6% every time they give you interest, but twice a year for 20 years, this guy would go to 40, wouldn't it? Essentially, we're doubling the number of interest periods. And we're up to 51,000. And lastly, instead of 120 months in 20 years, there's 240. Hey, by the way, you know this is exponential growth. So if you think about the curve for exponential growth, you know that after a while, it may grow slowly, but after a while, that puppy's going to turn and go. I did ask the question, did our money double? Our time doubled. So we let the money sit there twice as long. Did it double our money? Well, I went ahead and went back and pulled those figures from before. See, after 10 years, we had $15,000 in this case. After 10 years, we had 16. And after 10 years, we had 16 here. And notice that, no, it way more than doubled. Why? Because we're talking about exponential growth. And between two time periods, in this period of time, we don't have a whole lot of growth. In this, we grew from here up to here. But in this next time period, we had much more growth because that curve is just climbing faster and faster all the time. This stuff is actually really important for you first to understand just what's going on with exponential functions, but even more for your own personal finances, okay? So what if you compounded daily? You know, back in the old days when I was young, there were banks that did compound daily. Will that give me a lot more money? Should I pull my money out of Bank B and go over here to Bank C because they're going to compound daily? Well, sure, if Bank C's next door, but what if I have to drive 100 miles to get to this bank? Is it going to be worth it for me to do that? Well, what if then another bank comes along and says, well, we'll compound 1,000 times a year? Or somebody else says, oh, we'll just infinitely many times compound, which I know. It's like, what the heck? Well, watch what happens here. First, I put up an equation, I put up the formula as if we were going to compound this 1,000 times a year. So we would take our interest rate and divide it by 1,000 to get our periodic rate. And for however many years we let our money sit there, it'd be 1,000 times t is how many times they would give me interest. So this is how much I would have in the account. Now, I did a little bit of weird algebra. Okay, be patient with me. I did a little weird algebra. I said, how about if you take this fraction and multiply top and bottom by 1 over r? Now, you're totally okay with saying, why would you do that? Just humor me. In the numerator, I get a 1. In the denominator, I get a 1,000 over r. Now, I'm going to do the same thing up in the exponent in that I'm going to divide by an r and multiply by an r. Again, you say, man, this woman is just crazy. She's taking a mess and making it worse. I know. Just play with me. Okay? So I have that big, ugly mess, which could, if we decide to make it 10,000 times or 50 million times or whatever, as this keeps getting larger and larger and larger, this denominator is going to get huge. Likewise, this exponent is going to get huge. And you'll notice that I have 1,000 over r, 1,000 over r, and those values are the same thing here, raised to the RT power, and it came down just a minute early, but this became E. What? Well, back in the last lesson, I gave you a definition for E, and I said if you have 1 plus 1 over h, raised to the h power, as h gets hugely large, that's going to be what E happens to be. Now, the reason I'm telling you that is we sometimes have situations where we say you are compounding infinitely many times. Now, I know that seems crazy. You don't hear banks advertising that. But if you have, and the phrase that we use here is continuously. When we're talking about interest, if you see the phrase, it is continuously compounded, that means it's not a matter of, at a certain point in time, they computed your interest and added it in. In the case of continuously, you're constantly earning money. Okay, I know, it's a weird concept, but stay with me. But if that's happening, then you go from this formula, which is for finite compounding, over to this guy, which is for infinite compounding. Now, I went looking because, you know, my studying has been in mathematics. It hasn't been in all of these other areas where we have applications. So sometimes I go looking, you know, do we really do continuously compounded? Well, according to a little bit of reading I did, is that some of the high finance people say it scales real easily over multiple periods. Okay, whatever that means in high finance, they find using continuously compounding is real helpful in that. The other way that they use it in finance is that they say it's time consistent. And I guess that is to compare in investments, okay? So you'll have to talk to your finance people to see what these are really talking about, although my stockbroker said he doesn't really use E much. All right, so let's actually work a problem here. You're investing $5,000 in an account that compounds continuously. Yeah, right, like you're gonna find one of those. How much do you have in the account at the end of 1 year? Well, the formula we use is A equals A naught times E to the RT. So the amount that we have in the account would be my beginning amount, my principal. My R here is going to be my annual rate. Actually, you just have to make sure that these are consistent in their units of time. So if I put an annual rate there, and it still's the 12%, the time is 1 year. Okay? So what do we get? Yeah, I'm really not doing that one in my head. We get $5,637.48. Now, let's take a look up here. I kept this because I knew we'd want to go back and look at it. If I get interest once a year, it's $5,600. If they compound it twice a year, I get $5,618. Now we had monthly, which was something like $5,634 and some cents. Okay? Now this guy is $5,637.48. Do you see that we're not gaining a whole lot more by having more compounding periods? Yeah. In the beginning, they're more helpful, okay? And of course, over a long period of time, they're going to be very helpful. But you may not have to run around town to go from, say, monthly to 20 times a year. You may not see much difference. The other thing, which is actually answering my third question, what investment information do you gain from knowing this? It means that this guy is essentially your limit. It means that if you run the continuously compounded interest formula and you come up with this 56, 37, 48, it means that's the most you could possibly earn, no matter how often they're going to compound it. And that can help you make better choices maybe in your investments. Okay? Now I did want to run just one more here. What about at the end of 10 years? Well, the only thing I need to do is to change my time in my formula to 10, and we end up with $16,600. Okay? And I forget exactly what we had there before, but it was like $16,500 when we were compounding it monthly. So you can see that it made some effect, but not a huge effect. So don't get real excited about trying to demand continuously compounded interest from your bank. Okay? Oh, I actually wrote it up there. $16,501. This was the monthly over 10 years, and here's the continuously over 10 years. Now, another place that I think is a great application for continuously compounded is in the area of biology. And kind of like population growth ideas. Of course, your biology people will tell you that there's some limitations on that. That's why I don't do a whole lot with population growth with the exponential model, because I hope you realize that an exponential model on population growth only works for a short period of time, because then you start running into constraints from the environment. All right? But what I'd like to do is first off point out this phrase, uninhibited growth. Uninhibited growth is the same idea as continuously compounded. Okay? So we've got some gnats, and this population of gnats is going to grow continuously. And I think that makes sense for an uninhibited growth idea. It's not like they all wait to a certain point in time and then boom, there's the offspring all of a sudden. You're told that the average growth rate is, and I totally made this up, so I apologize, biology people. It's 8.6% per day. If you started with 500 gnats, who in the world counted those? How many should you have at the end of a week? Because it's uninhibited growth, I say I'm going to use A equals A naught E to the RT. I would have A is equal to 500 gnats is what I started with. And now you might recall I told you these units must be consistent. My growth rate is given as 0.086, 8.6% per day, which means my time needs to be in days. So how many at the end of a week? We'll put a 7 in there. Okay on the setup? Because I'm going to have the answer pop up here, so maybe right in the way. Yep. Let me remove that. It's 500 times e raised to that exponent, 912.88. And I'll let your biologists tell you whether you should make that 913 or 912. I'd probably claim I have 912 gnats at that point in time. That 913th one isn't quite here yet. Yes? Hey, I think all I have left is recap. So let me go back here and mention Rule of 72. And if we have a chance, we'll talk about something else as far as interest is concerned. The Rule of 72 is a very interesting way to approximate the amount of time to double your money. You will double your money in approximately the number of years, which is 72 divided by your APR. And by the way, in this case, you don't put it in as a decimal, you just remove the percent sign. So for example, on our 12%, 72 divided by 12 is 6. So it means that approximately every 6 years we will double our money. And I don't have all the figures here, but after the 10 years we had more than doubled our money. Okay? And if you have an interest rate of 8%, well then it's going to take you a little longer. You've got 72 divided by 8. It'll take you 9 years to double your money. Of course, what's interesting about this, and remember this whole idea of exponential growth, that means that if you started out with $100, and let's take 12%. After 6 years, it's $200. Another 6 years, it's $400. Another 6 years, it's $800. Another 6 years, it's $1,600. Now you might say, wow, that doesn't look very impressive. But wait a minute, you put in 100. The rest of that is all interest. And you can keep doubling, doubling, doubling. Hey, the last thing, and forgive me, I know that I probably shouldn't, but I always like to talk about the snow story. Here's the idea. If you've got a really long hill and you start a snowball at the top of this hill, as that snowball rolls down the hill, and I always think of a cartoon with cartoon characters getting caught up in it all, by the time it gets to the bottom, you can have this huge snowball. Now, I'm going to claim that there's 4 things that affect how big that snowball is at the end, at the bottom of the hill. So, what do you think is going to affect how big that is? Now, I've done this in class a lot of years, so I know a lot of the answers that you're likely to give me. You're going to tell me, well, the size of the starting snowball. You bet. That will have an impact on it. Some people say, well, the depth of your snow. Yep, I agree. A lot of people say, well, the height of that hill. Because you know, the farther that has to fall, the more snow you can pick up along the way. And the last thing has to do, maybe it's a little bit weird, but the steepness of the hill might kind of help with the packing down. Now, I claim that each one of these can get connected to some idea in our interest stories. The size of the starting snowball, well, that'd be my principal. How much I start out with. The depth of the snow, we know that affects how much my snowball grows every time it goes around. Well, that's the APR, or the interest rate. I'm just lazy. The height of the hill, it's time. The steepness, yeah, this one's a little bit weird. To me, this is the compounding, whether it's compounded semi-annually or monthly or whatever. Now, which of these features do you think has the biggest impact on how big that snowball is at the bottom of the hill? Well, if you think about it for a while, that time, which had a lot of impact on how many compounding or how many interest periods I had, that has the biggest impact because that's sitting up as the exponent. And what does that mean for you? Well, for your own personal life, here's a little help. Invest your money as early as you can. The longer you let that grow, the bigger you're going to see it become. And by the way, for a great example of that, go back and look at that putting pennies on the June calendar. Yeah, the big growth was at the end. Wouldn't you like to have 31 days instead of 30 days? Yeah. On the recap here, I've mentioned a couple of things about graphing, which were really back in our last lesson. Now, specifically to this lesson, for interest that is compounded on a periodic basis, I said use one of the formulas. Well, there's really only one official formula, but then there was that Mrs. Blanton formula where I said it's the beginning amount times 1 plus periodic rate raised to the number of interest periods. Now, if you have continuously compounded or uninhibited growth, then you're going to use the formula that has the E. And then one other thing that I do think is useful is that continuous compounding will give us the maximum we could earn at that given interest rate for that given amount of time, regardless of how often our money is compounded. So I hope you found these applications somewhat interesting, and I'll see you in the next lesson.